Hello, class. Today we are going to be teaching you about simplifying radical expressions. This is for our Algebra 1 slash Integrated Math 1 class. We are your teachers. I am Josh Ward.
I'm Matthew Alexander.
I'm Steven Scott.
Okay. First, we're gonna have we're gonna have the class do a warm up. So we're gonna have you do 3 questions. We're gonna have you do numbers 1 and 2, simplify each expression. So number 1 is find the square root of 9. Number 2 is to find the square root of 25. And the third question is to write 5 perfect squares. So we are going to give the class some time to do that. Once we gave the class some time, we would ask some students for some answers. And we would want the answer for number 1 to be 3. For number 2, the answer would be 5. And for the 5 perfect squares, we would want to hear anywhere from 1, 4, 8, 16, up to 100. We can keep going up. Uh, our standard and objective for the day. Our standard is to rewrite expressions involving radicals and rational exponents using the properties of exponents. And with that standard, our objective or goal for the day is to have students be able to simplify radical expressions in the form we have right here to the right. We would have the square root sign, having x being a number, and having n being the degree of the radical sign, which we will cover in this lesson.
All right, so just to review the perfect squares that we were talking about in the warm-up. So anytime you multiply something by itself, that's called squaring. So for example, 3 times 3, that's 3 squared. The little 2 that you see on the example, that means it's squared. Anytime you square a whole number, that's a perfect square. And then numbers that are perfect squares are things like 1, 4, 9, 16, so on. And one way you can remember what makes something a perfect square versus does not, if we were to try to make like a shape with each side being like representing a certain length, the perfect squares are the ones that look like squares. You can see like 6 would not be a perfect square. 9 is because you can make it 3 times 3. Next slide. Thank you. All right. Radicals are the opposite of squaring. Well, the opposite of squaring is square root. And these are shown with the radical symbol, which we have on the slide. So for example, if 3 squared is 9, square root of 9 is going to be 3. And we tried to visualize that for you on the picture to the right as well. There's other kinds of radicals too, or other kinds of roots that are all called radicals. For example, if something is multiplied by itself 3 times, like 3 times 3 times 3, that's cubing it. So the opposite of that is going to be a cube root. So for example, with like in this cube on our right, we have each side is 3, has 3 little cubes in it. And that would be like 27 little cubes inside the big one. So the cube root of 27 is 3. Okay.
All right, so but what happens if what's inside the radical is not like a perfect square or perfect cube? Well, we can simplify that using the product property, which says that the square root of AB is equal to the square root of A times the square root of B. This allows us to break it into pieces. And if we find factors that are perfect squares, we can use this to simplify it down, right? And this also works for cube roots as well. So for example, let's say we have radical 20, right? 20 is not a perfect square, but we do know that one of its factors 4 is. So what we can do is rewrite 20 as 4 times 5 within the radical, and then use the product property to rewrite that as radical 4 times radical 5, right? 4 is a perfect square, right? It's 2 squared. So we can rewrite that as 2 squared, and then the square root simplifies that down to 2. So we get 2 times radical 5, and then we can just kind of smush that together You get a simplified answer of 2 times radical 5. Okay, so you guys are going to be working on some examples on your own. We'll give you guys a couple of minutes to work on it, and then we'll bring it back together. Then they do it. All right, great job, guys. You guys did great. All right, let's bring it back together and let's talk about it. Next slide, please. Okay. Okay, so for radical 18, right, we know that 9 is a perfect square, right? We could break 18 down into 9 times 2, right? Using the product property, we could rewrite that as radical 9 times radical 2, right? We know 9 is the same as 3 squared. So the square root of 3 squared is going to be 3, right? And then we'll smush that together at the end, and we'll get 3 times radical 2. And we talked about it also works for cubes, right? So the cube root of 48, well, we know that 8 is a perfect cube, right? That's 2 times 2 times 2. So we could rewrite this as 8 times 6. Using the product property, we could split that up to the cube root of 8 times the cube root of 6. We know 8 is 2 cubed, so that simplifies down to 2. And again, we can smush that back together. We'll get 2 times the cube root of 6.
Okay, so one strategy that we can use to simplify radicals is we can use a factor tree to help us find perfect squares or perfect cubes. We can see here on the left, you can take 80 and like if we wanted to find the square root of 80, we can break that down into 8 times 10. And then we can break down the 8 even further. We can do 4 times 2. 10 can also be broken down into 5 times 2. And you can see like 8 and 10 aren't perfect squares, so that's why we had to break them down. But then 4 is. So we can go, basically we can break this into a bunch of different square roots multiplied by each other using the product property that Stephen mentioned. And now we have square root of 4 times the square root of, well, 2 times 2, that's 2 squared. So square root of 4 times the square root of 2 squared, and then times the square root of 5. And then now we can actually simplify those into not being square roots. Now it's just 2 times 2 times the square root of 5, which eventually gets us to 4 times the square root of 5. So now we're going to be working, now you guys are going to be working on an example, square root of 175. Remember, you can use your calculators to see if certain numbers can be divided from 175. So I'll give you guys a few minutes to do that. And then we're going to spend a few minutes doing that. All right, so let's talk about it. So we can break 175 into, so this is a great example of when to use the factor tree because 175, that's not a perfect square and it's kind of a big, scary number. So we can divide a 5 from that, get a 5, and then 35. 5 can't be broken down anymore, but 35 can. Let you guys figured out that was 7 times 5. So that means now, going to kind of the stuff on the right, we have 2 5s, so we can take out a square root of 5 squared, which is just going to be 5. And then that times square root of 7, that's the answer.
All right, so now we're going to do an example with a cube root. So we're going to do the cube root of 144. So this time with the factor tree, you're not looking for perfect squares or sets of 2. We're looking for either perfect cubes or sets of 3 of the same number. So we'll give you guys a couple of minutes to work on that. All right, then they work on it. All right, good job, guys. Let's bring it back together. Let's talk about it. Okay, so 144, we know that's the same as 12 times 12. So we can split that into 12 and 12. 12 and 12 aren't perfect cubes, so we can split that again, right? We know 12 is equal to 3 times 4 or 6 times 2, so I put both on there, right? And 3, 4, 6, and 2, none of these are perfect cubes, so let's break them down again. 4 is the same as 2 times 2, 6 is the same as 3 times 2. And if you notice, we have 3 2's here, so this is what we're looking for, right? Right, so we can split 144 into 2 cubed times 3 times 3 times 2, right? 3, 3, and 2 are perfect cubes, and there's not enough for them to make a cube, right? So we're just going to simplify that into 18. And then using the product property, we can split that to be the cube root of 2 cubed times the cube root of 18, right? And then the cube root of 2 cubed will just be 2. And then we can multiply that together to kind of smush it together. That'll give us 2 times the cube root of 18.
Okay, class. We have one more case to talk about. What happens when there's a fraction in the exponent? Well, that relates back to our radicals. When we have a fraction in the exponent, we can use this rule right here. If we have the square root of x to the m, and then, or if we look at the right side, x to the m over n, we would use m as our exponent and n as our degree of our roots. Okay, so if we look at our first example on top 16, 16 to the 1/2, we would use our numerator of 1 as our exponent and 2 as our degree of our root. So we see that on the next piece after the arrow, 16, and remember the default version of the exponent or the general version of exponent is always 1. So 16 to the 1 is itself, and the default or general version of the root is 2. So we don't need to write the 2. Just writing the square root bar shows us that it's the root 2. And then we know that 16 is a perfect square, so we can rewrite that as 4 squared. And then the square root of 4 squared, or 4 times 4, is just 4. Okay? And then this also works for our cube roots, right? So for 8, we would have 8 to the 2/3, okay? So we would have 2 as our exponent, so 8 to the second power, and 3 as our root, so our cube root. And then we saw earlier in one of our examples that 8 is a cube root. It's 2 times 2 times 2. So we could break our 8 squared into 2 cubes. That's a lot of 2's, but we see that right here in our next piece after the arrow. 2 cubed, 2 cubed times 2 cubed. Okay? And now that we have 3 2's and 3 2's, we can pull both of them out. 2 times 2, and we have 4. And no, they don't always equal 4. That's just the case we see right here. Okay, class. Now we're going to get into groups and have a little activity. We're going to get 2 sets of cards each, okay? One set needs to be a non-simplified radical and exponent, just like we were working with. We saw square root of 175 or other ones, right? And then another set will be the simplified match, okay? So we want to match all the pairs. So a couple more examples to show you before you work in your groups is we have the square root of 28 and 27 to the 1/3 power, okay? For 27 to the 1/3 power, we have to remember that 1 becomes our exponent and 3 becomes our cube root. So we will have 27 to the cube root, and 27 is also 3 times 3 times 3. So 27 to the cube root is 3. And then the square root of 28, we could rewrite as 14 times 2. And we could rewrite 14 as 7 times 2. So we would have 2 2's under our square root. We could pull those out, and we would just have 1 2 outside the square root. We would have 2 times square root of 7. So we would match these just like this. And that is your task, to match all the pairs, okay? And as we gave the class some time, we would ask the class, how did you match the pairs? What techniques did you use? Okay, what techniques did they use with the 1/3 power or the exponent power? Yeah, okay. Thank you. That's our presentation.
All right, thank you.
Thank you.